Hello, I'm Chad Hoag, and this is part two of a five-part series on artificial intelligence. In this part, we're going to talk about symbolic AI. This is the thing that people were thinking about back at the Dartmouth workshop in 1956. And we're mostly going to talk about theorem proving, although there are many other applications as well. Theorems are mathematical statements of things that we believe might be true, and then we write a proof to prove to ourselves that they are true. Not that they're likely to be true or that they make sense, but that they absolutely must be true. The average person only comes into contact with mathematical theorems when they take geometry, perhaps in 10th grade in high school. And the kind of theorems you prove involve things like this triangle here, where we can say, if I know that angle B and angle C are the same width, and I know that the length of the segment between A and B is the same as the length of the segment from A and C, can I prove some other things? And turns out you can. But this is the work of quote unquote real mathematicians are interested in proving things, not necessarily about triangles, but about anything that can be expressed mathematically, much of it very abstract. Writing a proof of a theorem seems like something that definitely requires intelligence, definitely requires thinking. That's why the people who got together at the Dartmouth conference were excited about trying to solve that problem. If they could write a program that could prove theorems, they could definitely say there's artificial intelligence involved here. There are a variety of ways we could work on something like this. They all involve representing things that are true in some way called logic. We're going to look at an example based on the simplest kind of logic possible, which simply says we've got propositions that are either true or false. And we've got a bunch of statements we can make about those propositions, such as this first one is saying either proposition P is false, or proposition Q is false, or proposition R is true. This statement over here, on the other hand, is saying simply proposition P is true. So we could start with a bunch of these statements that we are given. These are things that we know, just like in our geometry class, we might know the length of these two sides is the same. And we have some other statement that we're trying to prove. What we can do, one of many things we could do, is called resolution, where we take two of these statements, like the two that I described already, and we say, if this one's true and that one's true, then I can prove that this new statement that hasn't been written yet must also be true. There are a variety of rules of logic that will allow us to make those kind of decisions. And then if we know this sentence is true and this sentence is true, then we can conclude, therefore, that this sentence must be true. And if these two sentences must be true, then we can conclude that this sentence must be true. And if this sentence and this sentence are true, we can conclude that this sentence is true. And in fact, this example also uses something called proof by contradiction that we don't need to get into. But the point is, the way we can solve these problems is by simply saying, start out with a list of all the things that I think are true and see all the ways that I can combine them to prove other things that are true. And hopefully, if I keep doing that over and over again, combining statements, I will eventually end up proving the statement that I was trying to prove, and thus I will have a proof of my theorem. I can say this is true because of this, which is true because of this, which is true because of this, which is true because of this. When I describe it that way, does it sound intelligent? Does it really sound like thinking? It certainly sounds much more mechanical and uninteresting than what I imagine a mathematician doing when they solve a theorem or prove a theorem. But in fact, programs like this were written way back in the 1950s and 60s, and they were able to prove a great many mathematical theorems. So now that it's proven, or now that it's been done, we think, okay, maybe that's not AI. Of course it is, but it no longer seems like a thing that can't be done. Just seems like a thing that when we solve it, it just doesn't seem all that intelligent. This idea has then gone forward and accomplished many, many other things. One of the most important applications of this is in proving that software systems do what we say they do. It's one thing to test a software system, but testing can never uncover all possible problems because we can't test all possible inputs and all possible scenarios. However, if we can make statements we know are true about our program and use those to prove other statements are true, we will know absolutely that no matter what our input, these things can be guaranteed. And that's very nice. Another branch of AI that started a little bit later is trying to solve puzzles. Like this one, this is called the 15 puzzle. You may have played with one as a child. There are a bunch of these tiles here, and the tiles can slide up, down, left, and right. There's always one space that doesn't have a tile in it. There are lots of other puzzles that I could have put here instead, the Rubik's Cube, other things like that, but the 15 puzzle is nice and easy to visualize. So the way you play with this puzzle is you start with the tiles in some arbitrary order, and you try to get them to 1, 2, 3, 4 across the top row, 5, 6, 7, 8 across the second row, 9, 10, 11, 12, 13, 14, 15, and then the empty space. This picture shows one that is very close to being solved, but it's not solved. The 14 and 15 are in the wrong order. So how do you play with this puzzle to try to solve it? Well, you can slide a tile that is next to the open spot into the open spot, thus making the place that the tile you just slid had been open. So for example, we could slide the 12 down, making a space here. We could slide the 14 to the right, making space here. So this sounds like something that you need to be intelligent to solve, require a lot of thinking, but maybe not really. Here's a strategy that works that a computer can easily execute. We just imagine the future. And when I say the word imagine, it already makes us think like, that's definitely thinking. But imagining really isn't all that complicated. It just means saying, draw me a picture of what the world would be like if we slid the 12 down. Well, now the 12 would be here, there'd be an open space here. Draw me a picture of the world the way it would be if instead I moved the 14 to the right. The 14 would be here and the space would be here. If either of those is now the way we want our picture to look, then we've solved the puzzle. If not, then we just take each of those and say, well, imagine what if we did this second step. So if the first step we'd done was to slide the 12 down, we could imagine now either sliding the 8 down or sliding the 11 right. And why not try both? We'll just keep exploring all possible futures that we could get to by sliding blocks until we reach a possible future that has them in the right order. And then we just have to have remembered how did we get here, and that'll give me the sequence of actions, slide the 12 down, slide the left over, slide the 7 down, etc. This is, in fact, a perfectly good way to solve puzzles like this. As the puzzles get more complicated, we need to do more complicated things to perhaps worry about the order of which future things we're trying first to try to find the one that's going to work out faster than the ones that aren't. But this basic strategy works pretty well. Intelligent? Thinking? I don't know. That same technology is used by you probably every day, used by me almost every day when I get in my car and I'm going somewhere I've never been before and I ask Google to find me directions. It can say, well, here's where you are right now. Here's where we'd like you to be. Let's figure out a sequence of actions which are driving from one intersection to another that will get you there. And it just imagines a bunch of possible futures until it finds one that has me at my final destination. Soon after that, people started thinking, okay, well, we can look into the future to imagine how to solve these puzzles, but puzzles aren't very interesting. What about playing games? When you're playing a game, you can't just imagine the future based on what you're doing. You also have to imagine the future based on what an opponent is doing. And that makes life a whole lot more difficult. Or maybe it does. It turns out that chess, something that definitely seems like a game you would have to have a lot of intelligence and a lot of thinking to play, is pretty easy. By 1997, a chess computer named Deep Blue beat the reigning chess champion, the greatest grandmaster at the time, Garry Kasparov. And I believe no grandmaster has beaten the best chess computer program since then. Remarkable achievement. In fact, there's a much more complicated game than chess called Go. And in the time when Deep Blue was built, it was still not capable of playing Go at the level of an expert, though already far better than the average person. In 2016, the computer program AlphaGo beat the world's best Go player. And there's now, to my knowledge, no board game in which a human is better than AI at the top level. So how does this work? It must be fantastically complicated. Well, it is and it isn't. We continue to just imagine futures. It's just that now when we're imagining futures, we have to account not just for the times that we have decisions to make that we get to choose, but also the times when our opponent has decisions to make and they get to choose. And we need to choose our decisions in a very careful way that sort of boxes our opponent in to a situation where they will have no good moves. In a game like chess, there are many, 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 many possible futures that need to be discussed. In fact, we may not be able to look all the way to the end of the game, and we might have to make some estimates of how good a future is if it's not completely good, us winning, or completely bad, us losing. But computers can do that. And once you realize that it's just imagining a bunch of futures and picking the best one, doesn't really seem that smart anymore. This, of course, has applications all over the place anytime that you're trying to do something where you have an adversary and you would like to outsmart them. And then after a time, people combined these two ideas, the idea of looking into potential futures and the idea of representing things that are true in the world, and came up with this thing called automated planning, where we'll say, here's a description of the way the world is right now, written out as a bunch of statements and logic. Here's a description of the way I want the world to be, again, written out as a bunch of statements and logic. And here are a bunch of actions I can take. Each one has certain things that have to be true in order for me to do it, written out as logical statements. Things that are going to stop being true as a result of me doing it, written out as logical statements. And things that are going to start being true as a result of me taking them, written out as logical statements. And so we can imagine futures in a way that now is based on whatever my actions are defined as, whatever my initial and final states are. We can write a very general program that says, as long as you can describe your problem in terms of these logical things, my program will be able to tell you how to solve it. And eventually people said, all that AI stuff is cool, but it's all just happening inside the computer. You've got to tell the computer what's going on. You've got to get the computer's answer. We need machines that can directly sense the world and directly change the world. And so that comes to robotics, where all the kinds of things we've been talking about are built into a machine that actually has sensors that are detecting what's going on. It actually has actuators which are making changes in the world. So that's sort of our classical symbolic AI. Next time, we're going to talk about machine learning, a very sort of different topic, but all under artificial intelligence. See you then.